Welcome to Lecture 17b, and this lecture is on line integrals of vector dot products and particular applications. So we've been more or less have the fundamentals behind us, and now we want to actually utilize them to solve specific problems. So the material in this lecture is covered in section 1.5 of reading assignment 4 and followed by section 1.1. So the objectives are essentially the integration of contour integrals. At the end of this lecture, I'll explain a little bit more about the teaching pedagogy for the latter part of the course and the difference between reading assignment 4 and chapter 17 of the textbook. So the concepts and visualization skills are basically the tools required to solve contour integrals. That's a tangent vector in 2D and 3D and a normal vector in 2D. And we're basically then going to summarize with a summary of the two different interpretations of vector calculus, more or less a brief historical overview. So just two notes. The first is that this lecture introduces new material, and it's quite dense, as was Lecture 17a. So it's advised that you read the relevant parts of reading assignment 4 in parallel. And note too, I just alluded to this, that the last slide in this lecture is not mandatory reading, but it gives a historical perspective of vector calculus and makes you aware of the fact that the remaining part of this course is organized differently than chapter 17 of the textbook. We will not use chapter 17 of the textbook aside from the problems. All right, so as usual, there's an outline of the slides to follow. We'll just skip over this. All right, so we're going to now start with a simple illustration, and because we're going to do integrations, we're going to start with the Riemann sum for the area under a curve. We're now dealing with lines which are not necessarily straight anymore. And so the picture that you see here is a curve in the xy plane, and it's parametrized according to positions along its arc length. S is used to represent arc length. And also, there's a function which takes on different values at different points as we march along this contour. And so what we'd like to do is to compute the area of this, what I would call pleated curtain. So its height basically is changing, but in fact, it's not a flat surface, it's a curved surface. And so how do we go about basically determining area of this pleated surface? Right, so we would basically break this down into small rectangular elements. Each one of these would represent along a particular direction on the contour. So here would be like this, here would be like this, and so on. And we would take the mean height of the function between these 2 points to represent the actual height that we're going to use. And we're going to compute the area of this rectangle and then do it for all other rectangles, add them together, which would be an approximation to the area of the pleated curtain. So this is a more rigorous way of stating it. We're going to assume that C is a smooth curve of finite length, parameterized in terms of arc length as R of S, XS, Y of S, for A is less than or equal to S less than or equal to B. So this is more or less a position vector. It's mapping out points along the curve in the XY plane. And then we're going to subdivide this contour C into small n small arcs by forming a partition of A of B. And so A is on one extreme end and B is on the other extreme end. And so the area that you see on the pleated curve would be the height of the function at some mean value of S between 2 points, multiplied by the distance along that segment of the arc length, which would be here. So this is the mean height. Right here, mean height evaluated at some intermediate point, and sum this over all elements starting from here to there. So this would be the area basically under this pleated curve. This is a Riemann sum. All right, so then we can then come up with the definition of the scalar line integral in 2D and 3D, and this is in terms of parametrization in terms of arc length S. So a scalar valued function f is defined on the smooth curve, parametrized by the arc length S. The line integral of f over c is this expression, Again, notice that the number of elements goes to infinity, right? And at the same time, the width gets smaller and smaller. So in the limit, this expression just becomes integral over that curve. Again, this is provided the limit exists over all partitions of the contour C. When the limit exists, f is said to be integrable on C. We can extend this also to 3D, that is a curve in 3D. So the only difference here would now be that this would involve a third component, z, and this function now basically is being evaluated, with a z component in mind as well. And this would be just the arc length, but moving in a 3D direction. Now, if we were to try to put some meaning to height here, this would have no real physical meaning. It's just saying that you can extend the notion of integration along a closed curve, multiplied by some function, to 3D if you wish. And we'll use it in a different context, though. Now, the only problem here is S is an arc length, but it's not something that's necessarily calculable. So we would like to relate the arc length to something which is calculable. And so that's going to be the next step, so that finally we can do some computations. And we go back to our usual little problem in terms of tangent vectors. And from a tangent vector, we're going to be able to determine a normal vector. So we start with a simple illustration where basically a position vector is mapping out points on a contour. Now we're talking about contours. So at r of t, it's here. This is in terms of some parametrization variable, t. And this is what the position vector looks like at some time, at some t a little later, that is at delta t. If we take the difference between those two vectors, then it's this red vector that you see here. If you now let delta t goes to 0, that means you're bringing this blue line closer and closer. That effectively what you'll see is a delta r here, which represents the tangent vector that's tangent at the point P on that contour. And so this is just the dynamics here. This is showing the r of t is a position vector as a function of some variable t. Delta r is just the difference between the variable, the position vector, two different values of t, one at t plus delta t, one at t. And then by just a small trick, we divide through by delta t and multiply through by delta t. This expression is the same as this expression. And then write it in this form. And then we basically just say that in the limit, as delta t goes to 0, right, this becomes the arc length. This physical distance is the arc length, but it's a differential arc length. We give it the symbol ds. It's a vector. It's in bold. Sometimes we write it as dr, also in bold. And it's a limiting process of this. This now becomes the derivative with respect to time, a variable t, dt. And this is sometimes written also as r prime t or as r dot dt. This r dot just means a derivative operation, all right? I mean, it may not be with respect to t. In this case, it's implied with respect to t because there's a dt over here. Same here. All right, so now that we know that we can compute basically ds, and we know that the ds is a tangent vector times a unit tangent vector times the magnitude differential length, we can now basically move ahead and start to develop a framework that allows us to do the calculations. All right, so now we've got specific values to deal with. So we're going to do computations of line integrals, computing t using either what we call a parametrized or explicit representation of the contour. And so first step is to determine the position vector r that traces out the contour, open or closed, and the bounds on the variable t for what we call parametrized representation, and x for explicit representation. We'll explain what that means shortly. So parametrized for 2D would be just some position vector that has an x and a y component as a function of some variable t. In 3D, it would involve also a z component. And so any line can be represented by a single parameterization variable. If it's explicit, it means that we can relate the contour in the xy plane in terms of y as a function of x. So now everything's in terms of x. So in this case, basically for 2D, it's x and y of x. And in 3D, it'll be x, y of x, and z of x. That's the only difference. So the next step would be to compute the unit tangent vector, t, which would just be the derivative of the position vector divided by the magnitude of the derivative of the position vector. All right, so the vector r dot t tangent to the contour, right, is just a matter of taking the derivative of the position vector with respect to the variable. So in the case of parametrization, we've chosen t as our variable. So r dot vector is x dot y dot in a 2D case. In the 3D case, it would be r dot x dot y dot z dot. For the explicit representation, then we're dealing with now everything in terms of x. So if we take the derivative with respect to x, then for the case of 2D, we end up with 1. That's derivative of x with respect to x is 1. And derivative of y with respect to x is dy dx. And in the second case here, in the 3D case, we have also z components. So you're going to have a dy dx term and a dz dx term. All right, so the next thing basically would be to compute the unit tangent vector, which is to take the vector we just computed and divide it by its magnitude. And so for the parametrized case, right, you've got the expression here. The magnitude of this would just be this expression, and this is t, it's just that divided by that. For the 3D case, the magnitude of r now involves 3 components. For the explicit case, this magnitude just becomes the square root of 1 dy dx squared, and for the 3D case, this just has a dz dx squared term as well. Okay, so next thing to do then basically is look at ns. We've done t. We now want to determine what the unit vector normal to the contour is, using either parametrized or explicit representation of the contour. And so ns basically in this case would be the unit normal to the contour, and it can be pointing inwards or outwards. The vector ns points outward from the contour typically. That is, points to your right if you traverse a closed contour in a counterclockwise direction. And this is another one of these conventions that we're going to be adopting, okay? So if you're moving around a contour in a counterclockwise direction, look to your right. That is the direction in which the vector ns should be, unit vector ns should be pointing. So if you look at the first note below, you can show that the vector ns is normal to t by taking the dot product of ns dot t and proving that the result is 0. That's basically a means of verifying that we've chosen the right value of ns, and t you can obtain from the previous slide. So here, if you look at the expression, right, we have ns as y dot t and minus x dot. If you take this now and dot product with t, you'll get 0. The magnitude is not any different than before. If you look at this, it's going to be x dot squared and y dot squared. And the only question now is, well, is a minus sign on this side or is it on this side? Well, you can show that this formulation will have a normal vector pointing outwards from the contour given that you're moving in a counterclockwise direction around the contour. In the explicit case, right, we'll have something that looks similar, but in this case, you'll have a dy dx for the x component minus 1 for the y component. So in very quick order, we basically compute t, and from t we can compute what ns is. So this is basically all the information that's required. Again, just remember r is a position vector. Okay, so next step basically is let's compute the magnitude of ds. We've got t, we've got ns. We need now ds, the magnitude, the little. So, and we're going to do this for the parametrized and explicit representation of a contour. So just recall that, what is the position vector in 2D and what is it in 3D for the parametrization case and the explicit case. So essentially just a summary. And so now we can move ahead. So ds, parameterized, the arc length vector was r dot dt, and you can obtain that from 2 slides back. The magnitude of that would be just ds, and that would just be the magnitude of r dot vector dt. In the explicit case, it'd also be r dot, but in this case, the variable of interest is x. So it's magnitude of r dot dx. All right, so for the 2D contour, what is the result for ds going to be for the parameterized case? It's just x dot squared plus y dot squared dt. For the 3D contour case, it involves an additional term, z dot squared under the square root sign. And for the explicit case, ds is just the square root of dx plus dy squared, but you can factor out dx. So if you factor dx out of the square root sign, this becomes 1 plus dy dx squared dx. And similarly here for the 3D case, you can factor dx out, and you'll end up with 1 plus dy dx squared plus dz dx squared, and then outside the square root dx. Okay, so now let's look at a parametrized and explicit representation of the integration of a scalar function. All right, and so the scalar function basically are things we discussed in the last lecture, but now we're going to basically show you how the calculations are done. Now you'll notice on the left I've got ds, which is the magnitude of the arc length, differential. This is x evaluated at some point on the curve, y evaluated at some point in the curve. But in this form, this is unusable. But we know how to do the transformations. And so x will be now in terms of the parameterization variable t, y will be in terms of parameterization variable t, and ds, we've already computed, will be r dot dt. In the 2D case, it's basically this expression, right? So once you're given the position vector, that means you know what x of t and y of t are, then you can express the function f in terms of purely in terms of variable t, and this term basically also becomes a function of t, dt, and now you're integrating between a lower bound and an upper bound of t. And so when you're defining a position vector, not only do you need to know what the relationship looks like, but you need to know what the endpoints of the contour are. That would be TA and TB. If it's 3D case, then we'll have a third component here. But again, this is not usable. This is actually how it would be used. But the r dot t now involves the third term, that's z dot squared. So position vector will be known, derivatives can compute it, limits will be known, and so this integral can be performed. Okay, so what about the explicit representation in 2D? Well, explicit representation in 2D, basically, this now in terms of x. So this r dot dx, this r dot now is this term. All right, but x, this becomes y of x. So now everything's in terms of x. The lower bound is with respect to an x, an upper bound with respect to an x. For the 3D case, all we're doing is adding a z component, which is a function of x, and we're adding one additional term here, which is dz by dx squared dx. Again, position vector is given. These 2 points basically are known, and so all these things are calculable, in which case you can compute the integral. So, for example, examples in 3D, right, here's an example. If this is equal to 1, which let's say with no units, then this just becomes ds, which is the length of a curve, c, in units of meters. And so how would you implement this? You go back to if this were 2D, or as if this is 3D, you go back here, this will be 1, and you're just integrating this, dx. On the other hand, if it's a physical quantity, so this, for instance, could be something like, what is the mass density along this curved line in 3D space? Then at every point on the curve, there's a mass density which is kilograms per meter. So if you put this in, basically, you're integrating the mass density over the length of the curve, and so that would be the total mass of the curve. So these are now basically the ways we go about doing the calculations if we're dealing with scalar functions and integrating over an arc length. All right, what about circulation and flux integrals? Let's look at how they're going to be, how we work with them. So we look at the parametrized and explicit representation of the circulation and flux integrals. So let's take 2 examples, one in 2D, a 2D vector field, and one a 3D vector field. In the case of a 2D vector field, the x and y component of the vector field can be both functions of x and y. So if we deal with the circulation integral in 2D, we can express the circulation integral in the following equivalent forms. Notice here I'm making no reference to whether it's partial circulation or full circulation. I just basically, it's a general statement. So here, for instance, this would be considered a partial circulation because it's not closed, but still it has units of circulation. If we're dealing with a parametrized way of dealing with things, well, then t basically would be just a vector, x dot, y dot, right, dt, Okay, so that basically would be TDS. X dot, Y dot, vector, dt, and you're dot product with the vector F. And F will be evaluated at X and Y, but X and Y are valued at T. So you can see that the X component of the function will have X and Y components, but evaluated at T, X dot d dt, plus G of X t, Y dot dt. So all of this is a function of T. You integrate between a lower bound of T and an upper bound of T. If you put an explicit form, then dx ddt becomes dx, and dy dt becomes dy. But now we're using parametrization variable x, so this becomes x and this becomes y of x for f, and for g it becomes x of y and y. Since we're integrating with respect to y, we have to express everything in terms of the function y. Here we're expressing in terms of an integral over dx, so everything's in terms of x. So this is the correct way of writing out this integral in explicit form for the 2D case. Again, just recall that TDS was this expression for the parameterized representation, and it was equal to dx dy for the explicit representation. All right, what about the flux integral in 2D? All right, the flux integral involves ns, and so in this case we're going to have a y dot and a minus x dot. Okay, so there's the only difference, that these two get swapped and there's a minus sign. Otherwise, everything more or less is still the same. In the case of explicit, same thing happens. You can see there's a swap that takes place here and a minus sign. Again, that goes to the definition of what ns was, and we take the dot product. Again, here is the summary. NSDS is this expression, right, for the parameterized representation, and NSDS equals this expression for the explicit representation. For the 3D vector field, F, if we're doing a circulation, this would have no validity when we're doing for a flux, because we mentioned ns could take on an infinite number of possibilities. So in this case, the only difference is now that the t vector, or TDS vector, is going to take up three values, one for the x, y, and z components, and it goes derivative with respect to t's. This would be the explicit case. You can work this out. It will be three terms now instead of two terms. So effectively, we're just doing this expression again, but there'll be an additional term involving basically the function h. All right. In the explicit case, I've actually written it out. In this case, x, y of x, z of x, dx for that one. dy, notice here now everything has to be in terms of y, and lastly, everything for the last expression would have to be in terms of z to be able to integrate with respect to z. So this is effectively how the calculations would be done. Okay, so I'm going to summarize by just sort of giving you sort of a historical view of vector calculus, because, you know, I guess about 120, 140 years ago approximately, there were basically two competing theories. And the two competing theories were basically one where it essentially said, let's focus on 3D and 2D, and the other party said, well, wait a minute, let's extend this higher dimensions. And so the people who ruled the day were the ones that could keep things simple and explain it to people, not knowing that in future years, when you tried to expand to higher dimensions, you basically had real intuitive issues to deal with, and very few people could understand what was going on. Had we gone the other direction, it would be purely a game of marrying properties of objects through geometry with the axioms of linear algebra. And when you put them together, you end up with something which is self-consistent and can be expanded to higher dimensions in a very transparent manner, much easier to understand. Unfortunately, the theory back at that time was not well understood, and so when people decided which fork in the road to take, they took the route which is the easiest, which is called Gibbs formalism. So Gibbs was a famous scientist who essentially made major contributions in many fields of science. But then there are two different ways to look at this. You know, if we're going to use the Gibbs formulation, which is perfectly okay if we're dealing with 2D and 3D, we have a problem, because the book basically works in 2D, but assumes the existence of a z-axis. So to some extent, there's a sort of an inconsistency in the argument, and this has always been the concern, that you had to do workarounds to make things happen. Where that we call the bottom-up approach. The top-down approach, essentially, which is the way I'm taking things, is to essentially say, let's assume everything is in 3D, because then we can make use of vector operations, which are understood in 3D but have no meaning in 2D. And then we can force a 3D problem to be a 2D problem by setting the Z components to 0. And in doing so, effectively, we can formulate all the problems in 2D starting with 3D. It's much easier to prove things that way. And so that's the approach that we've taken. Anyways, you can read through this slide, to get a little bit more insight as to what was going on back in the late 1800s. And, nowadays, of course, the alternate approach is called geometric algebra has gained a lot of attention, and there are people trying to push for it. However, there's no need at this point to do it because the calculus that we deal with here using the Gibbs formalism is perfectly adequate and essentially is consistent with the other approach, except that it's difficult to extend it to higher dimensions and still understand what you're trying to do. So that concludes Lecture 17B. Thank you for listening.